Yes.
Okay, Mirko.
Thank you. So, my name is Mirko Jakovljevic. I'm from TT Tech, and I will. You can hear me? I just started too early, right? Okay. Yeah, sure. So, my name is Mirko Jakovljevic. I will present on spacecraft architectures based on deterministic Ethernet. I twisted the presentation because I saw that that many software people who are most interested also in some aspects of software design for such architectures. So I added few aspects which are interesting because we are talking about integrated systems. It's not a federated system, it's an integrated system which is integrated by deterministic Ethernet, where we have tens or hundreds of functions which use common and shared resources. So just one slide about my company. So my company is TT Tech. TT Tech is a very funny name. It starts from, comes from time-trigger technology, meaning time-driven communication, time-driven operation of the system, strictly deterministic operation of the systems. And the company is primarily founded to market deterministic networks. This was a time-triggered protocol at the beginning. Right now, the focus is on deterministic Ethernet. And my company is active in different programs, different industries, primarily focusing on level A systems, on certifiable systems, on commercial aviation, on automotive industry. One of our owners is Audi, so we are some sort of strategic investment of Audi and Volkswagen Group. They produce about 10% of cars worldwide. And our primary task here is to help them deliver active safety platforms, and also we are working on autonomous driving. So a set of applications which is highly critical, highly integrated, and require a lot of processing power. So focus is on distributed embedded platforms and networks. So network is just a part of this platform, of embedded platforms, and the objective is to design platforms which are supporting design of applications where we have strong software abstraction, where we integrate many functions, and we ensure that these functions are not clashing, taking resources for themselves, or do something we do not expect. We also have programs in the domain of flight controls. Here are some programs like Boeing 787, a distributed power generation, which is level A system, Bombardier C-series flight controls, Embraer flight controls, Airbus for cabin pressure systems, and also NASA Orion, which had a first flight with the baseline technologies from TT Tech at the beginning of this month. So integrated platform for us is a set of components, networks, computing modules, real-time operating systems, middleware, which is simply generic functionality which keeps all these functions running and helps them execute and provide their function. So our focus is primarily on this part, not on application, but on the embedded platform and deterministic network as a core component of such platform. Deterministic networks in general are very important because they allow us to provide manageable designs. We see frequently in applications that small differences at the network layer in a highly integrated system can influence significantly operation of different functions, but also a methodology and how we design system. Finally, this also has an impact on system architectures. So what we really want to do is to design an integrated system where we have a number of periodic real-time control loops. Some of them are real-time, some of them hard real-time. Periodic media streams. Also, to make it more complex, we have alarm and protection functions or critical event messages which can create some traffic bursts. So you have a network, you have periodic traffic, hard real-time, and then you have traffic bursts. And in addition, to make it even more complicated, you want to have some soft-time functions, which are basically non-critical functions, which can do whatever they want with the remaining part of the bandwidth or processing power in the system, which is not used by the critical functions. So this can be done if you have a platform which can support that. We are not talking about networks as a mean to move message from one point to another point in the system, because such an approach to design in a highly integrated system is it's not viable. It's very complex to manage. We're talking about network as a part of, as a core component of a broader platform, where applications are simply connected and completely abstracted from the underlying layers and topology of the system. So, resource sharing challenge in integrated systems. If we have hundreds of functions, different types of functions, they access all common resources, and we need to ensure that, especially for real-time functions, this resource sharing is periodic and non-blocking, and we need to ensure some sort of embedded system virtualization where every function has a feeling it is running on its own resource and is not aware of any other function in the system. So we need to ensure that we have, for critical functions, very carefully planned access to resources, and also in optimal situation that we have additional functions which can be added, which are not critical, which are not going to influence those critical functions, and can have some arbitrary traffic profile. In aerospace domain, there are so-called integrated modular avionics architectures or integrated modular architectures, which represent closed system with safety, time, and critical and real-time functions. And in order to design such a system, you need to know everything about every function in the system. So you need to understand what are the resource requirements for this function, traffic profile, communication profile, and you need to understand how every function works. What we can do and what is possible today is to design distributed IMA architectures, which is more similar to some sort of embedded cloud computing, where you have a number of resources in the system, and you can ensure that even in an open system, your critical functions are going to operate. So this type of system can be described as a mixed criticality system. It is very useful for design of reconfigurable and open generic architectures. And there are some other keywords which are very attractive, like scalability and integration of safety critical, hard real time, and critical and non-critical functions. Now, how networks influence system design? Network capabilities, first of all, influence the model of computation and communication. This is something we're going to discuss in a few slides later. But this is a concept of how you integrate time, perception of time at a network level and at the application level, and how networking layer is connected to the operation of different tasks in the system. After we define the model of computation and communication, then there will be differences in distributed software platform design, application software methodology, but also you will have significant differences in architecture design. Because typically when you design a system which is integrated, there will be always some sort of consideration, where are my limitations? If I use SCAN, I know what type of system I can design. If I use MIL1553, I have some other options. If I use Ethernet, I know what I can do and what I cannot do in the system. And if I use something that can run hard real-time, soft time, and there are no congestions or clashes, my architecture looks different, because now I can move functions from one box to another and can do completely new architectures. And both things will influence also system lifecycle cost, because depending on what type of capability you have for system design and how you do it, you will influence whole chain of system lifecycle costs. So today we have Ethernet in different programs, typically in non-critical applications. Sometimes completely commercial products are used. But the key question is, what is Ethernet really? Because people who are using CAN or MIL 1553 and other protocols typically see a protocol as some monolithic standard. With Ethernet, this is completely different. We have some common properties, and these properties can be adapted over time. For example, in the 90s, we had Ethernet as a bus technology with congestion management, which was different than what we have in 2000 or since 2000 with switched Ethernet, where we have a network. We do not have a bus anymore. And over time, we can add new services like quality of service, which is defined in 802.1q, like VLANs or similar. And concerning the standards, the standard devices for switching, the capability of a switch is depending on the list of services which are provided on the switch. So there are different switches, Ethernet switches. For this can be a desktop office switch, or it can be some switch for data center. They will have different services. If it is a switch for critical application, it will also have some different services. Common core of standard services plus some add-ons. For critical applications, we have two standards today which are supporting design of highly integrated systems. One is ARINC 664 and another is SAS 6802. This is so-called time-triggered Ethernet. ARINC 664 is AFDX. They are both hosted now with SA International, and they're used in aerospace, space, automotive, and transportation industries. The solution for space with Ethernet standards could be in domain of time-triggered Ethernet, because this is something. This is a standard which has been defined together with space and aerospace industry and designed for highly critical applications with strict determinism. And the standard was released in 2011. Right now, there's an IEEE activity which is related to SAS 6802, or at least it is referenced in IEEE standard. And now we see some sort of diffusion of know-how and knowledge in definition of IEEE TSN standards. On the other side, hardcore critical aspects of the standards are going to be implemented in CCSDS committees, and we expect this discussion. We expected this discussion to start in this year, but it's postponed for the next meeting for the 2015. So, how a critical standard or critical set of services can be added to Ethernet? Well, if we design a traffic class which can be defined as a plug-in for a standard Ethernet switch, then we can support communication which is strictly deterministic within Ethernet networks. With SA AS6802 or time-triggered Ethernet, there's support for startup, synchronous startup, synchronous recovery, robust fault-tolerant distributed clocking, and there's a foundation for design of scheduled and synchronous traffic classes. So this is just added to best effort traffic and to other services from Ethernet at layer 2. What we do here is we just add another traffic class which is completely synchronous, in fact. We emulate synchronous behavior by using exchange of asynchronous messages. So we have asynchronous nature of the Ethernet we generate fault-tolerant time base, and we can then schedule traffic in the network. So from point to point in a multi-hop network, you can send data with fixed latency and microsecond jitter. This is very important for design of hard real-time systems and hard real-time controls. In an integrated system, it is important that we have capability to split different functions and see them completely in isolation. After we say, when we say, let's say we have 10 functions in the system and they have their own needs, they have some virtual links, we would model them as a set of units which simply have point-to-point connections or point-to-multi-point unidirectional connections. This is an approach which is used in commercial aerospace industry, and this helps to define very easily applications which must be integrated into a system. After we define this point-to-point connection or multicast connections among different functions, then we can use tools to define configuration for the system which can support such set of circuits, so to say. In this case, we have virtual links. Virtual link is a concept which allows us to define exactly what is the timing and timing performance and quality of service for specific link or data stream in the system. After we have everything defined in XML, these tools will simply create a configuration which can support such communication in an Ethernet network. For that, you will need quality of service capability at layer 2 in switches and on the end system. There are two types of virtual links. One is ARINC 664 or AFDX, where we can define maximum latency. These are asynchronous stream without any synchronization, and there's a SAS6802, which is supporting fixed latency per virtual link and synchronous communication. In order to have robust synchronous communication, you need to have fault-tolerant synchronization within the system. And this has been designed in the standard. We have a synchronization which can tolerate multiple faults, which can tolerate Byzantine synchronization faults, and there's no search for best master in the system. So this means we can create really robust synchronization and system time for all participants in this type of network, and also for all devices, for all network devices. Also, if there are some errors, we can calculate exactly what is the worst case synchronous startup and recovery time for the system. We use two-step fault-tolerant synchronization. This is an algorithm which is simply where we define in a system up to 32 masters which participate in synchronization, generation of synchronization in the system. And this is then spread to everybody through compression masters. What we do here is we do not spread time from some central resource. We simply align all local clocks in the system among each other. There's an algorithm which is running. For example, if you want microsecond resolution, you would have some exchange of messages every 2 milliseconds. And in this case, as a background traffic, and in this case, the system will be synchronized. And if some of these units die or stop working or are switched off, you will still not lose the synchronization of the remaining part of the system. Important thing is you can have different types of traffic in the system. You can have synchronous traffic, you can have asynchronous traffic, and asynchronous traffic can be split into best effort traffic and also rate-constrained traffic or so-called AFDX traffic. This is the set of services from Ethernet, standard services from Ethernet, which are implemented on our devices. And we have also additional ARINC 664 and SAS 6802 services with different types of virtual links, which are essential for design of integrated systems. So when we design a platform, basically in integrated systems, it is easy to integrate applications only if they are completely abstracted from the underlying details. And we can do it through different virtual links, or we can even emulate shared system memory in the network through the exchange of state variables in the system, and with synchronization at the network level, we can create impression that they are accessing some sort of shared memory, which is conflict-free. So there are no conflicts in the system. For system architects who is trying to virtualize a system, embedded cloud, so to say, he will have 3 tools to support this very, very hard and tough task. One of them is model of computation and communication. There are only 2 ways or 2 models you can use. This so-called time-triggered architecture model, or loosely time-triggered architecture model. They're used also in commercial aviation for design of advanced integrated systems, and similar approaches are used in space. Then there's for computing, we use time and space partitioning, and there's a need to have robust bandwidth partitioning with virtual links. These 2 models have different approach to synchronization between networking operation and cyclic or periodic operation of functions which are running on processors or on computing units. With LTTA, this is asynchronous model where we do not have synchronization among units, but they use their own local clock to ensure that they have cyclical cycles and cyclical operation in the exchange of data. In this case, we need defined maximum latency. This is one model. The second model is we have synchronous network. We have the concept of system time, and synchronous operation of synchronous network is also supported at and synchronized to the operation of applications in the system. This is a model which is typically used in large aircraft like Boeing 777, while loosely TTA is used in ARINC 664 or AFTX-based systems. In our case, we can use both of these models in one system. So this is possible. So in this case, system designer defines what is his preference. And for specific applications, he will decide to use one or another. The difference between 2 types of virtual links and 2 models is, so asynchronous, this definitely can be only LTTA or loosely TTA, while synchronous virtual links can support both models and enable so-called embedded cloud. With asynchronous virtual models, we have real-time performance. With another one, with synchronous virtual links, we have system-wide hard real-time performance because we have fixed latency. We don't care how far we are really from the controlled object, because we know, independent of the traffic in the system, it will have always constant quality of service. And therefore, synchronous virtual links can be used in open systems or mixed criticality systems, while for closed systems, we use normally asynchronous virtual links. We can use also synchronous. So why is the separation and robust partitioning at the network level important? We actually generate or emulate equivalent to physically separated Ethernet networks. That's the goal. This simplifies the job. In this case, all my functions believe they run on their own network and they run on their own computing resource. And this is the ultimate goal of design of integrated systems. On this chart, on the left side, you can see a system which contains both non-critical and critical functions. They use time-triggered Ethernet switch. Every function, even though they are spread over several computers, every function believes it is running on its own system, is not aware of any of other systems in the functions in the system. And what is also important, VLANs, as we know them, these are priority-based mechanisms. They cannot support the virtualization of time-critical function in such setup. This is only possible with virtual links and synchronous communication within an Ethernet network. Time and space partitioning, this is something we already mentioned. And also we have a concept of system-level partitioning or system-level time partitioning. This would mean out of the whole set of network resources and computing resources, we can take a slice and give it to one function, making sure that this function always has all these resources in the system and cannot be influenced by any other function in the system. And now, when we talk about virtualization in the system, when you see or talk about clouds, we know what virtualization in the cloud means. This means you have a server which can run different applications. You can move applications from point to point, but this cannot work with real-time functions. In our case, using this small cookbook, you can design an embedded system where you can set it up as a sort of a cloud where you have critical functions and non-critical functions. You can use different models of computation and communication in one system, and there's a set of capabilities you need to have for all of these aspects. So the benefits of time-triggered Ethernet is this network is designed for n-redundant systems, fault-tolerant systems, which are, so typically we use it in double or triple redundant systems, but it's also possible to design n-redundant networks. It helps to reduce the complexity of functional interactions. We have built-in mechanisms for fault-tolerant synchronization. It is operating autonomously and with scheduled operation and submission or transmission of messages. We have critical function timing, which is defined at network layer for hard real-time functions. For all other functions, you can select different models and then basically use it as a background task, best effort task, or have some real-time capability. You can scale and define what you really want from the system. But this specific capability to define alignment among functions at the network layer and define how they interact supports design of less complex systems. Because of that, we can also simplify software design, because we can completely separate logical and temporal behavior of the function. We can have very simple function doing very simple tasks, no watchdogs, no busy waiting, no nothing, just performing some specific calculation, while the whole timing and temporal behavior is defined at the lower layers. So we have lower layers which define timing for execution of the function. Then we have fault-tolerant layers. We have very clean layering in the system, which is, again, reducing the complexity. And also we can enable design of flat distributed architectures which are generic and scalable. So I have a few slides on complexity. I can discuss these later. Now let's talk about use cases for such technology. One of use cases is launcher and launcher applications. We are working with ESA and also the OEMs in Europe on different architectures and architecture analysis. And here's one example how this type of network can be used in a launcher. Typically, we have a larger number of units which are connected by data buses in all the launcher models. In new generation of launchers, this should be a more integrated architecture, which is based then on time-triggered Ethernet. So there are different benefits in design of systems. Some of them we already mentioned. But we have single fault tolerance, which is handled by the communication network, and it helps in design of complex systems. Then we can design more easily modular embedded platforms, where we have one network configuration for different launcher configurations. We have fully deterministic and predictable performance in complex integrated system. Lower software complexity. We can use standard physical layers, which are pretty robust at 100 megabit. Typically on Orion, we use so Lockheed Martin and Honeywell and NASA are using 1 gigabit Ethernet interface. And the system is also composable, because after we define some virtual links and try to add another function in the system, we can set up a system which is not influenced by this new function. So we add a function, do not influence the operation of any other function in the system. So this simplifies greatly the integration. We call it composability. You can compose the system and not change the operation of other functions in the system. And also it is Ethernet and COTS-based. So this is a launcher application, which is actually not covering only control and different stages. It is also going to the ground equipment. And the key idea here is to have a completely integrated network where you can pull tons of data during the launch phase. After liftoff, the network splits into two networks and is operating alone. Then it goes up into the space, it splits again. Then it can connect to some units in the space, some other capsules, and these two networks become one network again. So this is something that is already supported by the operation of time-triggered Ethernet. There are services which support synchronization and connection and decoupling of network parts. So in human spaceflight application, we are going more into the direction where we have systems which are more similar to commercial avionics. Up to dual fault tolerance, which is handled by the protocol. Again, full determinism, full traffic partitioning, where we can combine platform and payload, meaning we can design fully integrated systems, unified architectures, where we integrate all the systems and subsystems, mission systems, safety critical systems, controls, audio, video, everything can go through one network, which is important for design of size, weight, and power reduced or optimized systems. So this is the architecture of NASA Orion, which is using gigabit time-triggered Ethernet network. And this is something that Mr. George Eager from Lockheed presented at a workshop on October 23rd, 2013 in Europe. So the mission was on 5th December. I think everybody heard about NASA Orion launch. So the key was to test different systems, but also to run and test electronic systems which are built into the capsule, and this was an autonomous mission, not commanded from the. So this means all the systems which have been in the capsule in the Orion crew module have been also operational during the flight. So we got some congratulations on this mission. As we worked with NASA since 2007 and 2008, we have signed NASA Space Act as one of few European companies. And also I mentioned system lifecycle costs and system lifecycle in general. In 2011, there was a statement from Charles Bolden who mentioned 3 technologies: composites, new propulsion, and advanced avionics networks. So, to be honest, I never heard of any person at that level mentioning any type of few wires, networking technology or similar. But obviously, there was a very positive feedback, even from his side, on those capabilities. So, satellite applications. This is more of a visionary discussion, because there are also some, primarily high bandwidth is very important for these applications. But we see that, for example, all these different systems can be integrated by using a switched network, high bandwidth, and concerning the reconfiguration of the system, we have different additional possibilities, because functions are not really, do not really need to be very close to sensors or actuators. They can be placed in any part of the system. So this could also support design of completely new architectures. Concerning components, right now we have IP which is designed for aerospace, automotive, and energy applications. It is used in different programs and projects. And based on that, we have worked on a stripped-down space IP core. This means we can scale down the core for specific set of space applications. We plan and work and have concrete schedules for design of radiation-tolerant FPGAs and radiation-hardened ASICs. So the key here is to design COTS components for space with time-triggered Ethernet networks. We also provide a set of products which support design of integrated architectures, and different teams can actually work with these products to design new integrated architectures and already write the software before these COTS components for space are available. So this is all from me for today. Thank you very much for your attention. And if you have any questions, I would like to answer.
Are there any questions? Yes. Hold on.
Okay, let me expose some ignorance here. I don't get it why anybody would ever want to have a synchronous network. And the reason that I don't understand why there'd be any value in this whatsoever is because, as I understand it, if you've got a system that has real-time bounds, and if you keep the resource that you're worried about, whether it be bandwidth or computation, cycles, under 60%, then there's guaranteed to exist a real-time schedule that will meet all those deadlines. And I just couldn't imagine the case of going into a safety-critical system where any resource is over about 30 or 40%. So assuming that I start out to do a system, and I know it's going to be reliability matters. Therefore, I'm going to keep my communication bandwidth and my compute bandwidth down under 50% utilization. Then how could there possibly be an advantage? And if you're suggesting that we should be designing with a much higher bandwidth utilization, how well do you find that works on actual systems? I find it doesn't.
So
work.
I can answer on. I'm not aware of any system which is using really more than on the network side. In commercial aviation, typically systems which are which have plenty of margin use 5 to 10% of the bandwidth. Now the question is, what happens if somebody comes with another set of functions, wants to integrate these functions? It simply doesn't work. Then you have too many constraints in such a system, which is correct. If you have 10 gigs and similar quality of service, then you can say, I will use 1% of the bandwidth. But then you again have another constraints, what type of physical layer is going to be used. Typically in an integrated system with Ethernet, you would have hotspots. And the general rule is, well, if I have a hotspot in my system where I use over 25% of the bandwidth on one line, and probably there are some other lines, then I have already a potential issue. I actually have too many constraints in a system where I have several hotspots. So you want to avoid those hotspots. You want to ensure that really critical functions get their portion of bandwidth, that you have this hard real time. Otherwise, systems start losing frames, and it's a pretty complex issue. You will not have a system where you have like 50% of the utilization. You have a complex network. You do not have bus. Network is a different beast. Okay, in the network you have a whole much more bandwidth because you have parallel streams running in the system. But another point is why this is important is the set of limitations you have if you do not have synchronous system. First of all, you have a problem with calculating precisely how much resources, how many resources you really need, especially if you have tens of functions coming from different companies which need to be integrated. This is experience from commercial aerospace. They feel the difference going from Boeing 777, which was completely synchronous design, to a more complex asynchronous design. I think I have here one slide, actually, which is talking about how many more states you have in a system. If you design a system which is synchronous, like some hot standby system, this is outcome of the analysis by University of Illinois. You have a system with 185 reachable states. As if it is a synchronous system, like a synchronous microprocessor, this is great. You can do it easily, you can test it easily. Then you'll have an asynchronous model which doesn't have any communication latency between components. So this is whole asynchronous system. You'll get over 3 million states. If you have varying latencies in the system, you will not be able to calculate that. Nobody knows how many states really are in the system. Now you need to test those states. And basically, you have always, in a synchronous system, you have always possibility, if you add another function, you might expose some specific bugs in the system, which you never know you have it at all. So there are different aspects of application of synchronous and asynchronous capabilities in the system, and different impact on resource use in the system. I can talk about that probably for an hour, especially on the virtualization side. Virtualization.
I still don't see where you're attacking the 60% limit. If it's below 60%, it will work. So why add the complexity of this synchronous and I mean, because what it does is you're adding into the solution space all of these controls and concerns about the synchrony. Whereas if instead, if you didn't have that, if you just go, we don't have time for your Ethernet, we only have Ethernet, or we only have Wi-Fi, then you just have to make sure that your utilization is under 60 is exactly one thing you worry about.
Yeah,
This, you have to worry about all of this stuff, scheduling. If this thing expands, who has to give it up? You know, what can run? You're introducing the possibility of hitting the limits in a whole lot of cases instead of just one. That's a lot more things to manage.
First of all, 60% limit. Where is this number coming from?
That's the it's just the this is the standard thing for rate monotonic real-time scheduling.
I might add maybe.
But are you talking about bus or are you talking about network?
Real-time, right?
Yeah.
This is a
I think we should discuss this offline.
No, just one bit of information. It is true that we want to have large margins in this type of system, but when you have an high integrity system, we want also to be tolerant to failure. And failure in the nodes is not always a node that stops talking. It might be also a node that starts talking much more than what it is supposed to be. So your margin is eaten by a node that is bubbling. And when you have a network like that, then this is prevented by the switch, if I'm correctly.
Yes, absolutely.
And then it allows you to be tolerant to this type of failures. While if you have a fully asynchronous network, it's much more difficult to prevent this type of things. But that was just one.
No, that's a good case.
I think this is a topic for a workshop.
It is. I think maybe a separate deterministic workshop
Yeah.
would be a good thing.
Yes.
Okay, thank you very much.
Thank you.